Hey guys, I'm Sam, and I'm a data scientist from Cogility Software. Today I'm going to be talking about the role of zero coding in the world of streaming analytics. Let me first kick off the talk by presenting to you an interesting piece of statistics. This is the percentage of human beings on Earth that actually know how to code today. That means that almost every piece of digital technology that we rely on and interact with every single day were built by only 0.29% of our population. This is an incredible feat in itself, but isn't it kind of sad that only such a small percentage of people get to contribute to the advancement of digital technology? Surely coders aren't the only people who are smart and have great ideas. Why is it so difficult for non-coders to invent and create new digital solutions? To answer this question, I think we should first understand how solutions are made. This is the process of computational thinking, and it's also how we generally solve problems in modern engineering nowadays. We're supposed to break big problems down into smaller problems, then we simplify and generalize a problem so that a solution can actually solve multiple similar problems. Then we analyze and find patterns and rules before we execute the solution. In our case, more often than not, it's writing algorithms and coding. It's a strategy that many great thinkers throughout history has adopted in some shape or form. For example, Aristotle and Isaac Newton, Albert Einstein. It turns out we didn't get here by accident. Studies have shown that our brains are actually developed in a way that makes us naturally gravitate towards this type of abstract problem solving. Most professionals in their fields, engineers or not, naturally tend to follow this type of computational process in their work without even realizing it. However, depending on the problem at hand, many people lack the ability to resolve this last step because nowadays it often requires some level of programming. Our role as programmers and data scientists is to implement and execute these otherwise abstract ideas and solutions for subject matter experts such as these. Unfortunately, big coding projects take a lot of time, and the 0.29% small talent pool, not to mention a smaller fraction of those that actually code for a living, makes qualified developers really difficult to find, and very expensive to hire too, and hence make things such as big data analytics unattainable to a lot of businesses. We've essentially made coding a prerequisite for contributing to advancement in digital technology. But imagine putting the power of data into the hands of people beyond the 0.29%. The amount of value generated will be tremendous. We're already doing similar things with website building services like Squarespace and Wix. Today I would like to convince you that with Flink, we can easily do this with streaming analytics as well. So, what better place to start than complex event processing when it comes to bridging the gap between abstract problem solving and programming? For those who may not know what complex event processing, or CEP, is, here's a simple example. In a future not far from now, let's say Skynet detects bells ringing. Then it detects a very dapper man in a tuxedo. It also detects a beautiful woman in a white gown. At this point, I'm sure we all know where this is going. Maybe it is also able to identify rice flying in the air. We all know what's going on here because we're humans, and our minds just automatically associate these seemingly unrelated events to a wedding through our past experiences. But to a computer, all of these individual events don't really mean very much to it. However, if we give it some constraints, like say if all of these events happened at or around the same time and place, we tell the computer to identify this pattern as a wedding. Now, the computer has become 1,000 times more effective and efficient at identifying weddings than a human being. Building on this wedding example, here's a more complex depiction of how CEP can be used. You can set numerous types of observations as events and propagate them through all sorts of different event patterns, and not just weddings, that we might be interested in capturing in our streaming data. The result of a pattern can become the input of another pattern downstream, and a pattern downstream can actually receive multiple event inputs from many upstream patterns as well. Many layers of interrelated patterns work together to distill our chaotic, observations into actionable intelligence in real time. So here at Cogility Software, we've created a no-coding platform called Cogynt. Cogynt allows users to graphically design their event patterns through a user interface, and these patterns are automatically translated into a Flink job under the hood. Event data streams through Kafka, while Flink reads from Kafka topics and propagates the data through Flink jobs that were generated by the user through Cogynt. And this finally generates a solution. Here are the basic building blocks needed to make CEP work in a no-coding platform like Cogynt. First and foremost, we need data. More specifically, streaming data, also known as our events. We can use events that are streaming from your IoT applications or transactional events, purchase orders, web clicks, etc., etc. You can even make outputs from your machine learning algorithms as an observational event in CEP. Then, you have your constraints. These are the things that actually lay down the ground rules for how your events will be related to one another. Multiple constraints and events will then produce a pattern, something we simply call event patterns. Finally, to make this tool even more useful, we must have the option of doing at least simple computations with these events. Simple things like aggregations, logical operations, filter, math, etc., etc. Let me demonstrate how this will work through a classic fraud detection example. By the way, this example was inspired by a former Flink Forward presentation several years ago by Eric Denouy from ING. I decided that it would be a good idea to take an example from an existing problem that had been solved in a conventional coding method and show you how it can be done with no coding. So let's begin. Let's say we're a bank and we have access to bank account information, including balance, the account holder's name, contact information, as well as when the account was first created. Obviously, as a bank, we will also have transactional information. Here, we're specifically looking at mobile bank transaction scenarios where it is possible for a perpetrator to actually get their hands on a stolen phone with a mobile banking app installed. In this example, we're interested in being notified when an account is suspected of being a mule account. A mule account is sort of a throwaway account that perpetrators use to receive stolen funds from their victims' accounts. Typically, as summarized by our subject matter expert from ING, there are three different types of patterns that we're interested in detecting. First, fraudulent transactions usually exceed a minimum threshold. Secondly, the mule account itself is usually newly created within the past 24 hours. And finally, the transfer is done repeatedly in a very short amount of time. So let's see how we can build a fraud detection system without code. This is Cogynt. What you're seeing here is the authoring screen for Cogynt. This is where our users create and design event patterns. For the sake of this demo, I've already created the event patterns that we will be using to help us identify mule accounts. Before we dive into the patterns though, let me first introduce you to the event types. Event types are essentially the window to your Kafka topics. As I mentioned earlier, the way Cogynt receives event data is through topics from Kafka. This means that our raw source data, in our case bank account and bank transaction topics, will need to first be instantiated as an event type before we can use them in our patterns. All pattern outputs will also need to be written to a unique topic so that downstream patterns can subsequently read from those output topics as event inputs. In other words, event types can both read from and write to Kafka topics depending on what role they play in your event patterns. As you can see here, I've already created event types for both our bank transactions and bank account topics. This event type here is reading from the Kafka topic bank account and is looking for fields listed here. Similarly, this event type here is reading from the topic bank transactions and will be looking for fields listed here. Now I've already loaded my local Kafka instance with these topics. They're just a set of randomly generated data with some engineered fraud cases inserted inside. So there's a way to actually double check and make sure that Cogynt is able to connect to your Kafka instance and read topics through our schema discovery tool. Sure enough, it is able to identify the two topics that we need. It is also able to read the schema of your topic and conveniently generate an event type if you hadn't already. Okay, now let's move on to the exciting part where we're looking at event patterns. Let's start by looking at the hierarchical diagram first. All right. Each of these little squares represent an event pattern. As we mentioned earlier, there are 3 signs to look out for when identifying mule accounts. First is that the transaction usually passes a threshold amount, and second, the perpetrator usually withdraws funds from the same source account repeatedly in a very short amount of time. You will see that we can actually combine these 2 patterns into a single pattern right here. Then you have another event pattern that detects whether the destination account of a transaction is an account that is less than 24 hours old. The output of these individual patterns are aggregated in this pattern called suspicious transactions. This is the pattern that determines whether an account is indeed a mule account. Because the upstream events individually do not indicate that an account is suspicious, it's the combination of these 3 criteria that make it suspicious. So this is the event that filters these suspicious accounts out. This final pattern here then groups all transactional information by mule accounts, so that when we visualize our notifications, we can actually see all the transactions that were ever associated with a single mule account. This allows us to assess the damage or take immediate action, whether it be sending notifications to our victims or to immediately freeze the mule account. So let's start with this pattern where we detect repeated transactions. This pattern takes in raw bank transaction event type as an input and publishes the results to the repeated transfer attempts output event type. To detect whether repeated transfers were being made between the same source and destination accounts, we need to partition our transaction data by source account and destination account. We're also interested in transactions within an hour window. Finally, we set a multiplicity of 3 plus to indicate that this pattern will only match if there had been 3 or more repeated transfers. Now remember I said that we can also fit the threshold criteria in this pattern as well? Well, it is as simple as filtering the transaction amount to a transfer alert threshold, which is really just a constant. I've already set this value to $1,000. Now in our output event, you can actually add computations to your event fields before publishing them to Kafka. Here we're doing a simple summation to the amount in the set of repeated transactions that were detected by our pattern. By including this in computations, we can determine the total cumulated amount of money this perpetrator has withdrawn from this source account and publish it along with this event. The rest here is simply mapping the relevant data that might be used downstream. Now similarly, in this pattern, where we detect transactions that are involved with destination accounts that are less than 24 hours old, the process is quite straightforward. Simply take your bank transaction stream and match the destination account to your bank account record and see whether the destination account was created less than 24 hours prior to the transaction time. Alright, now this is where everything comes together. For this suspicious transaction pattern to actually match, a bank transaction must satisfy both the repeated transfer pattern and the new account pattern that we were just looking at. Finally, to wrap everything up in a bow, we will group all suspicious transactions by our destination accounts that happen to be our mule accounts and copy over all mule account information because maybe we want to visualize this data in a nice dashboard or other visualization tools that you may be interested in using. So now I've already set up Cogynt to use my local instance of Kafka and Flink, as you can see here. So now I think we're ready to deploy these patterns. Let's give it a name. Awesome. Great, the job has been deployed. What happened here is that Cogynt took all these patterns that we have here and translated this into a Flink job. Let's take a look at the Flink dashboard to check out our job. All right, it's running. And there's the Flink graph. Yep, looks like everything is working just fine. All right, now it's time to verify that our Flink job is actually doing what we told it to do. So at this point, you can use whatever visualization tool you prefer. We happen to have created our own called the Analyst Workstation as part of our Cogynt platform. I've already set up everything in advance, so let's just dive right in. So we're interested in seeing all the accounts that were suspected to be a mule account. So let's toggle the mule account event type to start listening in from this topic. Now we need to tell it to create a notification whenever new events for mule accounts are detected. Good. Now we can open our dashboard and view our notifications. As you can see, Flink was instantly able to filter out all 3 mule accounts I randomly injected into our data. Each of these mule accounts were set to have 3 targets, and each target had 3 repeated transactions before our system supposedly caught and froze the account, making there a total of 9 fraudulent transactions for each of these mule accounts. Now, an interesting feature we have here is something we call a drill down, where we can trace all events that happened upstream that's participated in creating this particular notification, or in other words, tracing all low-level events and data that is related to the single mule account. You can select any of these events, and it will show you all the information that exists for each of them. This is especially useful for applications where human verification is required before action can be taken. This is a very convenient tool, especially for subject matter experts who doesn't really know how to code or would prefer to have everything all in one place visually without having to query a database. This about sums up the demo part of the presentation. I hope I've been able to demonstrate how simple it is to create event patterns and how quickly we can get results all without coding. Now that we've experienced how simple it is to build a complex Flink job through a no-coding platform like Cogynt, what does this all mean? I'm sure we're all part of this Flink conference because we appreciate the importance of speed when it comes to handling data. The value of data is highest when it's freshest. This means that we must take into account speed of development and our ability to pivot and react to change. A no-coding platform that can be used directly by a subject matter expert means that complex ideas and field-specific knowledge do not have to run the risk of being lost in translation. Enterprises will reduce development time drastically, become extremely reactive to change, which ultimately equates to cost savings and increase in productivity. That being said, no-coding platforms can only go so far as to generalize problems. There will always be unique and more complex situations out there where one might decide that they need more customizability and control over specific aspects of their problem. But for most 90% of cases, custom code is not really necessary. There are a lot of common problems out there that are shared across disciplines, and those problems are usually solved individually by a large team of developers. What if, instead of building custom software that will benefit only a single company, one of those software teams build the tools that empowers all types of businesses? The value from the work of the software team will now be compounded by all the businesses that can benefit from their tools and not just a single company. There is no doubt that the no-coding wave will arrive, and one can argue that we're already in it. I hope I've managed to convince you that there is incredible value in investing in no-coding platforms. For those who still have reservations about no-coding, here's some food for thought. Quoting from a no-code conference promotional video made by Webflow, imagine if only 1 in 400 people knew how to write. Think how many world-changing ideas that would have never come to light. We'd be stuck in the dark ages. And when it comes to software development, I think we still are in the dark ages. Web design has already taken the lead on this. Now I think it is our turn. Thank you.